Okay, it's my pleasure to present Raphaël Tinarrage, who is going to talk about the tension of representation orbits of compact Lie groups from point cloud. Take it away.
Thank you, Barbara. Thank you so much for the invitation. So this is a joint work with Henrique Ennes that I will present. And I would like to start with a simple observation that may perhaps seem surprising at first. I take an image here that I rotate. It's a 2D image. And I embed this whole collection of images into the Euclidean space by flattening the images. So we end up into R to the m times m. So this is the number of pixels times 3, number of channels. It's a RGB image. And so the point cloud we get is highly structured. And you can see that from the eigenvalues of its covariance matrix, as you will do with PCA dimension reduction, for instance. And as you can see, the eigenvalues come as pairs. So we actually have eigenplanes. And if I project this point cloud into the eigenplanes, I represented the first 4 here, you will observe circular orbits, right? So each eigenplane is attached with a certain radius that depends on the eigenvalue and a certain frequency, okay? And what you can show here is that actually this point cloud lies very close to this curve here that is a representation orbit of SO2, the circle group. And so the eigen vectors will be these images here that I took back to the initial image. And so this curve here in pink is the output of the algorithm that I will present. It is the representation orbit of SO2 that fits the best this point cloud. So this is a case where we already know we observe a linear orbit, but you can play this game the other way around. You only observe a point cloud and you ask whether it is supported by a linear action of a Lie group. So I take here as an illustration the 3-body problem. You have 3 planets, equal masses in the plane. What you expect from such a system is a chaotic orbit, usually. But in very specific configurations, you see periodic orbits. So this one is called A3, has been found by Brook. And so what I do, I take the positions of the 3 bodies, concatenate them. So we have a curve in R6. And we applied the algorithm to find this very well-fitting pink curve that is nothing but a representation orbit of SO2. So I'm not claiming here that the 2 curves are equal, because that will mean that this solution of the specific solution will be written as a simple sum of sines and cosines. I don't think it is the case, but still interesting, I think, to observe this very close fit. And so more generally, this is the problem we tackled that I formulate like that. We have an input, a point cloud X, and we seek a compact Lie group G, a representation of this Lie group, and an orbit of this representation that will fit the best the point cloud. And we will focus specifically on these groups here, SO2, the circular group, T2, the torus, and SO3, the rotations of the space. And these are actual outputs of the algorithm. But first of all, let me recall a few definitions for those who are not familiar with the theory. A Lie group, this is a manifold that is also a group with compatible structures. So you have a few examples here. the general inner group, the set of invertible matrices. We will focus also on this spatial orthogonal group. The torus, so the D torus, I see it as a product of D copies of SO2. Okay. Now, a representation of a Lie group, this is a group morphism, a smooth group morphism from the group to the invertible matrices. And so we say the group acts linearly on Rn. So for instance, all these groups here, as you can see, are matrix groups in the sense that they are defined as subsets of the matrices. And in this case, you have a canonical representation, which is simply the inclusion. But you have also more fancy representations. For instance, for SO2, any integer, omega, will yield this representation here in R2. So this is a rotation that turns omega times in the plane. So what we usually do when we have a representation is try to decompose it into irreducibles. A representation is said irreducible if it does not stabilize any non-trivial subspace of Rn. And so I call that an irrep. And the important fact is that every representation is, up to a change of basis, equal to a sum of irreps. You can find a matrix A such that the conjugation is equal to the sum, the concatenation, if you wish, of certain irreps. And so this decomposition is unique. So for these classical groups, the irreps are well known. For SO2, for instance, apart from the trivial representation, these are what I presented, rotations in a certain number of times in the plane. So they are indexed by this omega. For the torus, same thing, but then you have several variables, but you just take a linear combination of several frequencies now. And these are the irreducible representations of the torus, still of dimension 2. For SO3, you have one irrep in each odd dimensional Euclidean space. And for SU2, one irrep for each odd dimensional n dimension multiple of 4. Okay, and now the protagonist of this talk, the notion of orbit. So you pick a point in the space and you let the group act on it via the matrices of the representation, and this draws the orbit of the point. So how does that look like? For SO2, for instance, in dimension 2k, to simplify, take a representation, decompose it as a sum of irreps, so it looks like that. And so the orbit will be this curve that winds a certain number of times in each of these orthogonal planes. For the torus, same thing, but you have now several parameters. Each irrep is indexed by d frequencies that we call weights. So you can just gather these frequencies in the matrix. And the orbits now will be topologically tori. And our last example is SO3 and SU2. You can also decompose into irreps. And you will obtain orbits of dimension 3, generically, if you choose correctly the initial point. All right, so we can now come back to our problem and ask a first question, the question of identifiability. So we only observe an orbit, or maybe just a finite sample of it. Can we go back to the representation that gave rise to it? So in general, this is not possible. And this is because several non-equivalent representations may yield the same orbits. An example here is given by SO2 in R2. If you turn once around the plane or twice, you will have the same orbits, circles. So the notion of equivalence of representations is not what we need here. We need the notion of orbit equivalence. And I say that two representations are orbit equivalent if after conjugated the first one, you obtain the same orbits. Okay? So now you can try to classify representations with respect to this new equivalence relation. For SO2 in R2K, you will find that they are described by the primitive tuples of integers, with trivial GCD. For the torus, so this naturally generalizes as the primitive lattices. And for SO3 and SU2, so actually the notion of equivalence and of orbit equivalence are the same thing. Okay, so now the main tool we have to study representations is through the notion of Lie algebra. I recall that to every Lie group is attached a Lie algebra. So this is a vector space that is endowed with an additional structure called the Lie bracket. Okay, this is a sort of product that satisfies some axioms. But in the case of matrix groups, you can see this Lie algebra simply as the tangent space of the group, seen as a submanifold of the matrices, at the identity matrix. And moreover, the Lie bracket in this case is nothing but the commutator of matrices. So for instance, GLN is an open submanifold of the matrices, so its tangent space will be the full space, okay? Let me just say that, yeah, we use this Gothic font to denote Lie algebras. For SON, this will be the set of skew-symmetric matrices. All right. Now, with the Lie algebra comes an exponential map. So this is a map from the Lie algebra to the group. Okay, you can understand that as the Riemannian exponential map. And it is surjective when the group is connected and compact. Okay. So now what we can do is take our representation and derive it. So we will obtain a linear map between Lie algebras. It will actually be more than that. It will be Lie algebra morphism. And moreover, we will have that this diagram commutes. Yeah. And now there is something very interesting we can do, is take this Lie algebra of G and push it via this derived homomorphism. This will give a subalgebra of the matrices, GLN. And as it turns out, this push-forward Lie algebra is all we need for the problem of orbit equivalence. Namely, it is a direct consequence of the definition that two representations are orbit equivalent if and only if their push-forward Lie algebras are conjugated via an invertible matrix. Okay? So really the space we should work in here is the space of subalgebras of GLN, okay, that I call the Grassmannian of subalgebras of GLN. We have an action of the general linear group on that, and the quotient will be the orbit equivalence classes of representations. So the object we want to estimate now, our new problem is to estimate this push-forward Lie algebra. But I recall you that we only have access to the orbits. So what can we do, only knowing the orbits? There exists an intermediate space that contain the Lie algebra, the pushforward Lie algebra, and this is called the symmetry algebra. So given the orbit, I can define the symmetry group. This is the set of matrices that stabilize the orbit. This is the Lie group. It has a Lie algebra, and this is called the symmetry algebra. Okay, and the important fact is that we can find the push-forward Lie algebra inside this space. Let me suppose for the next few slides that they are actually equal to simplify, but I will show you how to get rid of this assumption. Our new problem is to estimate this symmetry algebra. And there is precisely an algorithm that allows to do that. It's been published 2 years ago by Cahill, Mixon and Parshall. This is called LiePCA. So let me show you how that works. X is our finite sample. And so the authors define an operator, lambda, on the space of matrices as follows. To a matrix A is associated this sum of products, where you can see here projection matrices onto the normal spaces of the orbit. So if you only have a finite sample, you can estimate that with local PCA, for instance. And also projection matrices on the lines spanned by the points of this point cloud. And the important result that I write informally here is that the kernel of this operator is approximately the symmetry algebra we're looking for. So a bit more formally, this operator is symmetric. You can diagonalize it. Its eigenvectors will be matrices. And so the idea is that eigenvectors associated to small eigenvalues will be this symmetry algebra. An example here, I sampled a few points on the flat torus in R4. I computed this LiePCA operator and its eigenvalues. And you can see two significantly small eigenvalues. And this is precisely the corresponding eigenvectors will be precisely the symmetry algebra of the flat torus. And so in the original article, the authors propose to estimate, give an estimation of the symmetry algebra by taking these bottom eigenvectors and the space they span. Okay? So this works very well, but won't be enough for us. And this is because LiePCA only estimates this symmetry algebra as if it were a vector space. You don't have guarantees regarding the Lie algebra structure, the Lie bracket. And ultimately, what we want to do is to exponentiate this Lie algebra and reconstruct the orbit. But now, if you have small discrepancies at the level of the Lie algebra, after exponentiation, you may have significant errors, okay? So really, what we want to do here is to take this first guess and convert it into a Lie subalgebra, project it onto the closest Lie subalgebra. So I wrote the problem like that here. The minimum over all Lie subalgebras of GLN of dimension D, the minimum of this distance, okay, for a certain distance on the Grassmannian. So let me rewrite this problem. All that I presented was in the case where we assume that the push-forward Lie algebra is equal to the symmetry algebra. But at this point, we don't need this assumption anymore. If the push-forward Lie algebra is only a subset, we can consider this problem. So this is the minimum of the values of the LiePCA operator on the Lie subalgebras. So what this quantity means here, it is so this quantity will be very small when the Lie algebra is close to the kernel of lambda. And so we have a natural generalization of this problem above. So let's try to implement that. Natural idea will be to embed the set of Lie algebras into a matrix space. So for instance, you can convert a subspace into the projection matrix on it. So you end up in the space of matrices of size n squared times n squared. And reformulating a little bit the problem, we will obtain something like that with a few constraints. So these first 3 constraints means that the matrix is a projection matrix on a d-dimensional subspace. And this last condition means that this subspace is a Lie subalgebra. You have a well-defined bracket. So this may seem like an innocent problem, but it is actually pretty intractable, because what is hidden here is the classification of Lie algebras, and this is an involved combinatorial problem. So what we really need here is to incorporate our knowledge of Lie algebras, and so this is what we will do. From now on, I will fix a Lie group G. Then I can restrict this Grassmannian to those Lie algebras that come from a representation of G. We still have an action of the general linear group by conjugation. And now this quotient will be in correspondence with the orbit equivalence classes of representations of G. And to implement the algorithm, I will choose arbitrarily and explicitly representative for each of these classes. And now I can take this second problem here, restrict it to this space, and I obtain this new formulation when you can see now 2 variables that appear. The first one is an orbit equivalence class of representation of G that I encode through its Lie algebra, decomposed in a decomposition into irreps. And the second one is a continuous variable that indicates the orientation of the representation. And well, this is a discrete continuous problem. For each orbit equivalence class, you perform a continuous optimization, and this is how we implemented the algorithm. There is one nice trick we can use here. We can apply a pre-processing step called orthonormalization that allows to reduce the optimization over only the orthogonal group. So this is good news for us, because this first manifold is open, is not compact, and has dimension n squared. And this one is compact and has dimension n minus 1 over 2. So this will help the implementation. All right, so this is a visualization of how the algorithm works. You go through all the representation orbit equivalence classes of SO2 here. The black dots represent a sample of an orbit of SO2. There is a problem with the abelian groups. Let me say that in sufficiently high dimension, you will find an infinite number of orbit equivalence classes of representations. So we need to fix a limit. So we have a maximal frequency, which is 4 here. And so the algorithm works at the level of the Lie algebra. And for each orbit equivalence class, find the best orientation to fit the kernel of lambda. And here I represent in pink what you get by exponentiating. Okay. Same example here.
Sorry, I have a question about the previous. So if I understand correctly, each of them is a possible orbit, and you're trying to fit and see if it is the correct one?
Yeah, all
Okay.
so this point cloud, I know it comes from a representation,
Mm-hmm.
but I don't know which one. I don't know
Yeah.
its type. So
Mm-hmm.
we just parse all the possible representations.
Sorry, yes, sorry. You go through the representation, not the
Yeah.
orbit. I pronounced it wrong. I mean, I said it wrongly, but I meant, yes, the representation.
Does that answer the question?
Yes, thank you. And actually, I have another question.
Yeah.
So the plot on the right, is it telling me about the convergency?
Yeah.
Okay.
This is,
Okay.
okay, yeah. So this space, so we are in R4.
Mm-hmm.
So this reduction of the algorithm to the orthogonal group allows to only consider Lie algebras generated by skew symmetric matrices.
Mm-hmm.
And the 4 by 4 skew symmetric matrices, if I'm not mistaken, has dimension 6.
Mm-hmm. I
Uh,
trust
it's 4 times 3 divided by 2. And this is what I represent here.
you.
The it's 1 point in dimension 6. This is the generator of the Lie algebra.
Mm-hmm. Okay. Thank you.
Welcome. And now, so yeah, if you apply this algorithm for an orbit of SU2, the Lie algebra is dimension 3. So I represent the same thing here. The, I represent the frame, the Lie algebra. And this must be the correct representation here, because we have a nice fit. Just a word about implementation. The first problem, given a first guess, find the closest Lie subalgebra, we found some reductions in specific cases. So for SO2, this boils down to a Procrust problem. So this can be solved exactly. For the torus, this can be reformulated as a simultaneous reduction of matrices, which is implemented as an optimization over ON. So optimization over ON just as the initial algorithm, but this optimization is easier. First, you do it only once, not for each representation type, but also the cost function is more easily calculated, and so it's a significant gain in practice. And for the non-abelian groups, we did not find reductions. We just applied the algorithm as I showed. Okay, let me maybe skip this technical pre-processing step, but basically using the fact that the group is compact, we can convert any representation to an orthogonal representation. But we can talk about that later if you wish. Let me present instead the final description of the algorithm. So now in the input, you have a point cloud and also a Lie group, a candidate Lie group. And so it is naturally divided in 4 steps. You have this orthonormalization pre-processing. Step 2, you compute LiePCA. Step 3, you find the optimal Lie subalgebra. And the last step, we reconstruct the orbits. So you choose a point of your point cloud, take the orbit, take the Lie algebra that you estimated, exponentiate it, and apply it to the point. And so this will create an orbit. And as a sanity check, we compute the Hausdorff distance between the point cloud and the estimated orbit. We actually compute the one-sided, the non-symmetric Hausdorff distance, the distance from the point cloud to the estimated orbit. This is because the point cloud may be sparse, it may have gaps, and we don't want to measure that. In the case where the point cloud is too noisy and you don't know what initial point to choose, we have a measure theoretic solution. So instead of computing one orbit, you compute all the orbits, take the uniform measure on these orbits, and take the average measure on that. And so the output now is a measure, and the sanity check consists in computing the Wasserstein distance now between the point cloud, so the empirical measure on the point cloud, and the output. Okay, let me show you an example where these sanity checks are important. This is an experiment where I sample 3,000 spatial orthogonal matrices, 3 by 3, and I embed them into R9. And I look for an action of SO3 on this point cloud. So if I apply LiePCA, I will find 6 small eigenvalues. And this is precisely the dimension of the isometry group of SO3, which is this product. Now I can apply the optimization step of the algorithm, and I will find 2 representations, 2 orbit equivalence classes with a very small cost. The first one, when you exponentiate and reconstruct the orbits, gives a very large Hausdorff distance. And the second one gives a small Hausdorff distance. So what happened here is that we actually found the action of SO3 on itself by conjugation, which is not a transitive action. So there is no hope to reconstruct the point cloud from only one orbit. And the second one is the action of SO3 on itself by translation, which is a transitive action. All right, so we try to obtain stability result for the algorithm, something like, say the point cloud is good enough, then the algorithm will succeed. And to do that, we found that it was very convenient to reformulate all the algorithm in a measure theoretic framework. So instead of a point cloud input, we have a measure input. So for instance, it may be the empirical measure on the point cloud. Now, the underlying orbit, we see it as the uniform measure on the orbit. And then you can reformulate all these steps for measures. And this is very convenient because it allows to use tools such that averaging on the groups. And we ended up with a theorem like that I state informally here. The hypothesis we need is that the Wasserstein distance between the input and the underlying orbit is sufficiently small. And if you have additional assumptions, then the algorithm will succeed, meaning that you find the correct orbit equivalence paths. And we have also bounds on the quality of the estimated orbit, either through the Wasserstein distance or with the Hausdorff distance. And the actual result looks like that. We have explicit bounds for each of the quantities involved, and this is based on some geometric quantities associated to the orbit. And additional technical hypothesis. Okay. So to conclude the talk, I would like to present a few applications. The first application is a machine learning problem. I build a data set as follows. I take a 3D image that I rotate all around in the space and embed the collection of images into the Euclidean space by flattening, just as before. So we end up in a high dimension, and I project this point cloud into Rn via PCA. And so the problem is the following. If I give you a point of this point cloud, can you estimate the unit vector of the space, of the initial space, that points toward the head of this animal? This is represented here. And so we divided the cloud into 90% train and 10% test. So how to solve that? Well, you can pick your favorite regression technique from machine learning, for instance, SVM. But we propose another solution. If you choose the embedding dimension here n to be 8, then the point cloud will be close to an orbit of SO3. This we found with our algorithm. And thanks to this diagram now, what we can do is pull back the point cloud to the Lie algebra of SO3. So how do you do that? You fix an initial point. For any new point, you look at the best vector in the Lie algebra that would send the initial point to the new point. I do that in the fundamental domain of the Lie algebra, so it looks like a cube. And so here is the representation of the objective function, this vector that points toward the head, seen in this new representation, this new encoding of the data. And as you can see, this function looks well behaved. Everything looks well separated. And so what I did, I trained the SVM on this. And these are the results. So SVM depends on the embedding dimension. So I did that from dimension 3 to 10. And as you can see, the greater the dimension, the smaller the mean squared error as expected. And actually the best score is obtained with this method that I presented, which is in the end only a 3-dimensional encoding of the data that uses only 8-dimensional information. Let me just say here, my point is not that we obtain the best score with this method, because I guess one could train a better model and obtain better scores. My point is that these ideas can be used to improve already existing methods. And yeah, so let me present another application with the famous cyclooctane data set. So the molecule of cyclooctane, as any molecule, admits conformers. So a conformer, this is realization of the molecule in the space. They can have different shapes, the atoms have different relative positions. And so to encode such a conformer, what we can do is simply list the position of all the atoms. So you have 24 atoms and 3 coordinates per atom. And so a conformer can be seen as a point in R to the 72. Now, a lot of conformers will give us a point cloud. And as it has been shown, this point cloud exhibits this intriguing topology, which is the union of a sphere and a Klein bottle. So this is well known. And so the question we had was, does this space admit a linear action of a Lie group? Do we have more than just this topology? So we'll present two versions of the experiment. In the first experiment, I generate a lot of conformers, but I do not align them yet. If you take this point cloud in R72 and visualize it, you will see something like that. So it looks like a tube with a belt, with a circle, okay? So we will try to separate these components. So what I did, I projected into R4. So we lose a lot of information, but not that much actually, because if you look at the eigenvalues of PCA, of the covariance matrix, they vanish very, very quick. But yeah, it's an important reduction. So now we are in R4. I will apply this orthogonalization step and perform the most simple clustering you can think of. I remove a few outliers and apply single linkage hierarchical clustering. I end up with these two clusters, and I will take the big one, the red one. I compute LiePCA, and I saw two small eigenvalues indicating the potential linear action of the torus. And indeed, after optimization, we found this orbit of the torus that fits well the point cloud. Now, let me do the same thing, but first aligning the conformers. This is what you're supposed to do with this kind of conformational spaces. So the topology will change, but we apply the same technique, reduction in R4, discard a few outliers, cluster the point cloud. Here we have three clusters, and I will take the red one. Now, LiePCA only shows one small eigenvalue. And so we actually found here only an action of SO2. So SO2 generates curves, one-dimensional orbits. So the action is not transitive, but it is well defined in the sense that for any point of the point cloud, if you generate the orbit, the curve will lie in the point cloud. And so an action of SO2 that do not lift to an action of T2, the torus, is what you expect from a Klein model. So what I think is interesting here is that in addition to the topology of this space, we can also see that there are some algebraic relations in these coordinates, right? Seen through linear orbits. And I think my time is up, so I will conclude. So there is a preprint on arXiv. It's not the last version. I will update it soon. But all the experiments I presented, you can find them on Henrique's GitHub. And this is it. Thank you.
Thank you, Raphaël. Now I will ask everybody, as usual, to unmute themselves and clap for the speaker. Thank you. And I was about to say, let's start with a question, but there is already a question in the chat. Can you please comment on the computational complexity of your algorithm?
So let me go back to the algorithm. The computational complexity. So the two main the main step, what is more costly, is really this optimization or ON. So in practice we do that with PyManopt in Python. It's a package for optimization on manifolds. And we use that up to dimension 15, basically 16, and above that, the optimization does not work very well anymore. Maybe I can show you. I have a slide that collects a few results here. So this is so we implemented the algorithm only for the tori, including SO2, for the SO3 and SU2. And these so these tables collect the running time of each run of the algorithm and the success also. So as you can see, it's, the higher dimension, the faster it gets.
Yeah, I have the suspicion that the question was more about the theoretical complexity, but I must say that in persistence, especially, we always have that the worst case complexity is a thing, and then the actual computational complexity is a completely different thing. So I think this is answering your question. From the same person, we also have what kind of machine you use it for your computations. I assume Sohail, if I pronounce it correctly, is talking about like the actual laptop or desktop or.
Yeah, this is my laptop, my personal laptop. Nothing too fancy.
Okay. Do we have other questions? Feel free to raise your hands or unmute yourself.
I also had a question about the algorithm. So, first of all, great talk. I enjoyed it. Thank you. So your objective is a 4th degree objective in A, if I'm not mistaken, and you're optimizing over the orthogonal group. So do I need to be worried about like spurious local minima when I'm using PyManopt?
Yeah, yeah, this will be a problem. And you can see that on this table. For instance, an orbit of SU2 in dimension 7. So if you have a point cloud dimension 7 and you ask for an orbit of SU2, what possibilities do you have? The representation, the irrep of dimension 7, and you have also 3 and 4, 3 plus 4, the concatenation of those. And as you can see, the algorithm succeeds 90% of the time. And it gets only worse in higher dimensions. So yeah, this is a problem. We did not try to improve that. It's very the basic parameters of PyManopt that we use.
Okay, thanks.
Are there other questions for the recorded part of the talk? Okay, then thank you, Raphaël. And then now I'm gonna stop the recording